Okay, hello class. Welcome to Physics 390 class 14. This class will be on spin. Spin is a type of angular momentum which has no real classical counterpart. So we're going to be looking at an analog of spin in classical systems, and then quantum mechanical spin, how it's described, and the special eigenvalues that the spin can take, which is different than the orbital angular momentum values, which we saw for the hydrogen atom. And then finally, we'll take a look at a couple of examples, one for a electron in a magnetic field, and which precesses around the magnetic field, and finally, deflection of particles with spin in what's called the Stern-Gerlach experiment. So this comes from chapter 4.4 of our textbook. Okay, so we just hinted, there's two kinds of angular momentum, and we'll talk about those in a second. And we're going to also be talking about the intrinsic spin angular momentum in quantum mechanics. So classically, an object has an orbital angular momentum, L equals r cross p, which has to do with the motion of its center of mass. It also can have a spinning angular momentum, S for spinning, equal the I omega, where I is the moment of inertia and omega is the angular velocity. And that's for motion around its center of mass. Okay, so as an example, if you think about the Earth's year has to do with its orbital angular momentum around the sun. So the center of mass of the Earth rotates around revolves around the sun, and that gives us the year. On the other hand, the Earth's day comes from the spinning of the Earth around its own center of mass, that is its own axis, and that spinning gives us the daily cycle. So you can see that there's two types of angular momentum for the Earth, which is a classical sized object. Now it's kind of interesting. Classically, the spinning angular momentum can actually be viewed as orbital angular momentum of little bits of the object around its own center of mass. So if we look at the object as a whole, we can say it has a spinning angular momentum. But if we divide up the object, say the Earth, into little pieces, then the S is really a sum of a bunch of little L's of all those little pieces around their own center of mass. So really, there's only one kind of angular momentum in classical mechanics, which is r cross p, but we can find a nice expression for it in terms of the moment of inertia and the angular velocity when it's a rigid body rotating around its center of mass. Okay. So in quantum mechanics, elementary particles, like for example, the electron, can have orbital angular momentum L if they're bound by a proton, say, in the hydrogen atom. And we saw that orbital angular momentum L is associated with the angular variables theta and phi in spherical coordinates. Okay, so in quantum mechanics, we can definitely have orbital angular momentum L. But in quantum mechanics, an elementary particle always has a spin angular momentum S, which it turns out cannot be viewed as it is classically as orbital angular momentum of bits of the particle around its center of mass. It's an intrinsic spin angular momentum in quantum mechanics. It's an intrinsic property of the particle. It's not derived from orbital angular momentum of little bits of the particle, like the electron, around its own center. And because of that, because it's not associated with orbital angular momentum, where we derive that the eigenfunctions of orbital angular momentum in quantum have spatial coordinates theta and phi, spin in quantum mechanics is not associated with the angular variables theta and phi, okay? It's going to have its own representation, which is a little bit different, but really interesting. Okay, so building a theory of spin angular momentum in quantum mechanics. So how do we do this? Well, just like with orbital angular momentum in L, we associate operators with the components Sx, Sy, and Sz of this intrinsic spin angular momentum S, okay? And we postulate that these operators have the same form of commutation relations as we found for Lx, Ly, and Lz for the orbital angular momentum in quantum. That is, for example, Sx, Sy commutator is IH bar Sz, and so on, permuting the three. So we have these guys to work with. Okay, so we start with these as our postulates. And then by similar arguments to what we put forward for the orbital angular momentum, we define raising and lowering operators, which were L plus and L minus, but now since we're dealing with the spin, it's S plus and S minus, and there's still Sx plus or minus Ixy. And by doing a number of arguments of what those raising and lowering operators must do to eigenstates and limiting the range of possible eigenstates, we find that the eigenstates, which were, remember, they were Lm for the orbital angular momentum, now they're little sm because it's spin s. They satisfy this. The eigenstates are simultaneous eigenstates of the square of the intrinsic spin angular momentum. And so simultaneous eigenstates of s squared and also of the z component sz. So we can get simultaneous eigenstates of those two, not sx, because sz doesn't commute with sx or sy, we can't get simultaneous eigenstates of sx or sy here. So the eigenvalues here are similar to the eigenvalues we saw for orbital angular momentum, which were h bar squared L times L plus 1. Here it's h bar squared S times S plus 1. And this one, Sz, is actually exactly the same. It's h bar m, where m is the quantum number for the z component of the spin angular momentum. Okay, so, but because these eigenstates, these simultaneous eigenstates, are not spherical harmonics, okay? Remember, they're not associated with theta and phi because the intrinsic spin is not built up of smaller amounts of orbital angular momenta. It's its own intrinsic thing. In that case, we can have half integer values of this quantity S, which are consistent mathematically with the analysis. So S can be, whereas L can be 0, 1, 2, 3, S can be 0, 1 half, 1, 3 halves, 2, 5 halves, etc. M here still runs from minus S to plus S. So for example, for S equals 0, M would only take the value 0. For S equals 1 half, it would run from minus S 1 half to plus S plus 1 half. So there'd be two values, minus 1 half plus 1 half. And we'll look at that system in a second. So the other interesting thing is, while the quantum number L can change, so the orbital angular momentum can change. So for example, if we have an electron in a hydrogen atom and we shoot a photon in, it can knock it up to a state, an excited state with a different value of L. Say we go from the ground state with L equals 0 to an excited state with L equal 1. We've changed the orbital angular momentum quantum number. But the quantum number S is fixed for a given particle. So so far as we know, there's no interaction with other particles, which is going to change this quantum number S for a given particle. However, it's different for different particles. This S, this quantum number S, which defines the total spin angular momentum. For the pi meson, also known as the pion, S equals 0. For the electron or proton or neutron, S equals 1 half. For the photon, S equals 1. And there are other examples. I believe the graviton, which is a hypothesized particle, has S equal 2. But so we're going to concentrate now on, since the electron and the proton and the neutron are so important in making up the basis of matter and the hydrogen atom and other atoms, we're going to concentrate on the S equals 1 half case. because the way we build it and the mathematics of it are similar to the other cases. And it's the simplest non-trivial case because we only have two m values, -1/2 and +1/2, as we'll see. Okay, so the important case of spin s equals 1/2. For s equals 1/2, we have two eigenstates, Sm. That would be s, again, s is 1/2, so it'd be 1/2, m equal 1/2. We call that spin up. And then 1/2, m equal -1/2, we call that spin down. So there's two eigenstates, okay? So whereas for the infinite square well, when we looked at the eigenstates of the energy, we had an infinite number. Here we only have two eigenstates, okay, two eigenstates. So we should be able to build any spin wave function from just these two eigenstates. So these form a basis for general spin s equal 1/2 states. And so the terminology we use this chi plus to represent the spin up state, where we have the 1 up here to represent spin up, and then chi minus to represent the spin down state, where we have the 1 below to represent spin down. Okay, so this 1, 0 represents this state right here, and this 0, 1 represents this state right here in this. So we're in the, these vectors are in the basis of these two states, with the top number, the spin up state, and the bottom number, the spin down state. Okay, so the general state, which is often sometimes called a spinner, because it's like a vector, but it's representing spin, so spinner, can be written as chi, which is some amount of spin up, which would be A, and some amount of spin down, which would be B. So expanded out, this would be A times the spin up state, 1, 0, plus B times the spin down state, 0, 1, which you can check if you make these vectors, they would add up to AB. Okay, so this is the general state. It's specified just by two numbers because we only have two eigenstates here. Okay. All right, so in this basis of spin up and spin down, the operators s squared, sz, sx, and sy actually become 2 by 2 matrices, okay? And the reason for that is because there's only two states. So if we take the matrix elements of these operators between the eigenstates, we only have 4 possibilities. Spin up operator spin up operator spin down, spin down operator spin up, and spin down operator spin down. So there's only 4 possible entries. So we have 2 by 2 matrices. So the operators are 2 by 2 matrices, as opposed to a variable like x, or an operation like the momentum minus I h bar ddx. They're actually matrices because this is a finite system. There's only 2 eigenstates to it. This is what the matrices look like. And you can see the text for derivations on some of them. A couple of them make a good amount of sense. A couple of them you need to work a little bit to get. But so s squared is 3/4 h bar squared times the identity matrix. And that kind of makes sense because for s equals, this top element is the matrix element of the spin up state with s squared and the spin up state. And if we operate on s equals 1/2, we get 1/2 s times s plus 1 h bar squared, which would be 1/2 times 3/2 times h bar squared. So that would be 3/4 h bar squared. And the same thing for spin down, we get s time, because that has the same s value of 1/2. We get 1/2 times 3/2 is 3/4 times h bar squared. So this is s squared, the 2 by 2 matrix representing s squared. Sz, well, Sc is going to be h bar over 2 for the spin up state, since the eigenvalue of the spin up state for the Sc is h bar over 2, and minus h bar over 2 for the spin down state. And then zeros across the diagonal, or off the diagonal. Then the other two are a little bit harder to get, but I'll just present them here. You can check the textbook for the derivation. Sx and Sy actually have no diagonal elements, and the off-diagonal elements are either 1, 1, or I minus I for Sy. Okay, so those are the matrices we have. So if we measure Sz for a state psi equal AB, we're going to get we have two possibilities. We'll either get plus h bar over 2 for spin up when we measure it, or minus h bar over 2 for spin down, because those are the two eigenstates of Sc. And the probabilities are going to be just like in the for the wave function squared is the probability. Here it's the component of the component of spin up, which would be A squared, will be the probability of getting plus h bar over 2 spin up, and B squared, which is the probability of spin down, or minus h bar over 2. Okay, so what does that mean? But those are the only two possibilities, right? We've got spin up and spin down. Those are the only two eigenstates of Sc, so we've got to get one or the other. So the total probability that we have must equal 1. So that tells us that a squared plus b squared is equal to 1. And this is, by the way, a and b can in principle be complex. So this would be the modulus of a squared and the modulus of b squared is equal to 1. And we call this the normalization of the spinner, the spin state AB. So a normalized spin state will have a squared plus b squared equal to 1. Okay. All right. So we can measure Sc naturally. What about Sx? Well, Sx is an interesting case, and it brings up the uncertainty principle. Okay. So it turns out if you do an eigenvalue problem, the eigenvectors of Sx, which is this matrix here, which we just looked at, one's on the off diagonal. If you find the eigenvalues and the eigenvalues are the same as the eigenvalues for Sz, plus h bar over 2 and minus h bar over 2. But the eigenstates are no longer 1, 0, and 0, 1, as they would be for Sc. They're 1 over the square root of 2, 1 over the square root of 2 for the plus state for this Sx plus, and then 1 over the square root of 2 and minus 1 over the square root of 2 for the Sx minus state. Okay, so we have the same two eigenvalues, but different eigenvectors. So these are expressed in the basis of the spin up and spin down for Sc. So this would represent 1 over the square root of 2 times spin up plus 1 over the square root of 2 times spin down. Okay, for the eigenstate of Sx with eigenvalue plus h bar over 2. Okay, so the state AB, which was we looked at before, which was A times x plus bx minus, where those x plus and x minus are the spin up and spin down states, it turns out can be written in the Sx basis in terms of these Sx eigenvectors, x plus x and x minus x, or chi plus x and chi minus x, as a plus b over square root of 2 times chi plus x plus a minus b over square root of 2 chi minus x. Okay, so we can see one of these. Let's see. So let's see. If we take this x plus chi plus here, we get 1 over square root of 2 times a over square root of 2, a plus b over square root of 2. So a plus b over 2 times chi plus, but then over here we get a minus b over 2. So we get a plus b plus a minus b over 2, which would be 2a over 2, or a over 2 times chi plus. Sorry, 2a over 2, or a times chi plus. Okay, so you can check if you write out these eigenvectors in the basis of the SZ basis that when you multiply them out, you get A times chi plus B times chi minus. If you just write these guys out as 1 over square root of 2 chi plus 1 over square root of 2 chi minus, and substitute them in here and multiply all out, you'll get this same thing here. So this is just re-expressing the same spinner in a new basis, the SX basis. Okay, but what does that tell us? Well, like from before, we know that if we express the state in terms of a basis, and SX is a observable, so this is a complete basis, so we can express any function. There's two eigenstates for SX. So there's two possibilities for measuring SX in the state chi. Either one of the two eigenstates, which have eigenvalues plus h bar over 2 or minus h bar over 2. And for this state we have here, the probabilities would be the square or the modulus squared of what we have in front of the SX eigenstates, x chi plus x and chi minus x. So taking the first one for plus h bar over 2, which is associated with this eigenstate, we have a plus b quantity modulus squared over 2 when we square it. So we have this probability. Then we have for this one a minus b over squared modulus squared over 2. Okay, so these would be the two probabilities we have. Okay, so if we take a special case, so this is a general case where we have a mixture of our state chi can have a mixture of spin up and spin down in it. If we take our state chi to be spin up, then looking at this formula here, A would equal 1 and B would equal 0. Okay, so A would be 1 to pick out spin up, and B would be 0 to not pick out spin down. So A equal 1 and B equals 0. If we plug that in, we have 1 plus 0 over 2, 1 plus 0 squared over 2, or 1/2 for the probability of plus h bar over 2, and 1 minus 0 squared over 2, or 1/2 for SX equal minus h bar over 2. So the probabilities for getting SX as plus or minus h bar over 2 are each 1/2 if we put a spin up state, a spin up with respect to the SZ basis. Okay, so we can either get plus h bar over 2 or minus h bar over 2 with equal probability if we put in the spin up state for the SZ basis and measure SX. So we can say SX is uncertain in the spin up state chi plus, and as we said, it takes on these values plus or minus h bar over 2 when it's measured. Once we measure it, the spin state will collapse or be set into either if we get plus h bar over 2, we'll have the new state will not be spin up. It will be the chi plus for the x state. So it'll be the equivalent of spin up, but in the x direction. On the other hand, if we got minus h bar over 2 for SX, it would be in the chi minus x state, which would be the equivalent of spin down, but in the x direction. And so the spin state becomes that state, and further measurements of SX would give the same value for SX, okay, because it's already in one of the eigenstates. Once we've measured it and it moves into that eigenstate, it will remain in that eigenstate, assuming it's not disturbed. And further measurements will give the same value for SX. And then SZ then becomes uncertain, okay, for the same reason as measuring SX for the spin up state in the SZ, x chi plus. If we have, say, chi plus x, if we measure SZ, if we did the analysis, we would find that there'd be a 1/2 chance of getting SZ equal plus h bar over 2 and SZ equal minus h bar over 2. Okay, so really interesting. And this is all a reflection of the fact that SX and SZ don't commute. okay, as we saw when we looked at the commutation relations. And we know when two things don't commute, they can't be known with certainty at the same time. So if we know SZ is plus h bar over 2, so we're in the spin up state, then SX is uncertain and it can be either with equal probability plus or minus h bar over 2. If, on the other hand, SX is plus h bar over 2, say, then SZ, when measured, will either be plus or minus h bar over 2 with equal probability. Okay, so they can't be known with certainty at the same time. They don't commute. Okay, let's take a look at a couple of physical examples here using this spin stuff. So we're going to look at an electron in a magnetic field and look at something called Larmor precession. So it turns out a particle with spin s has a magnetic dipole moment, which we call mu, equal to gamma times s. Okay, and gamma is called the gyromagnetic ratio, magnetic because it's giving rise to a magnetic dipole moment. And that gyromagnetic ratio depends on the particle. For the electron, it turns out to be just a little over 2, and its units are coulombs per kilogram. Okay, so we multiply the spin, which would have units of angular momentum, times this coulombs per kilogram, and that gives us something in units of magnetic moment, which is current times area, so amp meter squared. Okay, so why does it have a magnetic dipole moment? Well, it's basically it's a angular momentum, and an angular momentum of an orbital angular momentum is of a particle. A charged particle has a circulating current, and that circulating current will give rise to a magnetic dipole moment. So it turns out intrinsic spin also has a magnetic dipole moment associated with it, equal to this gamma times s. Okay, so in a magnetic field B, it turns out the energy of the magnetic dipole moment is minus mu dot B, minus the magnetic dipole moment dot B. And that favors alignment of the magnetic dipole moment with B, because if these two vectors, the magnetic dipole moment and B, are aligned, then the dot product will be positive and will have a lower energy, a negative energy. On the other hand, if they're not aligned, if they're in opposite directions, mu dot B will be a positive number, and we have, mu naught B will be a negative number, but minus mu naught B will be positive, and the energy would be higher. So this favors alignment. And then we can plug in, if we want, for mu, gamma s dot B. So the energy, or the Hamiltonian, of this quantum system is minus gamma s dot B. Okay, so let's take a particular B. We'll just say it's in the z direction. We usually use the z direction. So it's B naught z hat. So we get h equal minus gamma times s dot B, which would be s is sx as sy as z, but B only has a z component, which is B0. So it picks out SZ. And we get minus gamma times B naught times SZ. So gamma and B naught are constants. There's a constant magnetic field in space. And this gamma is a constant. So this is proportional to SZ. So this Hamiltonian, this energy operator, is going to have the same eigenstates as the SZ. It will just have different eigenvalues because it's multiplied by these two constants. So the eigenstates will be spin up and spin down, chi plus and chi minus, and the energies will be for plus minus h bar over 2, which is the eigenvalue of SZ. Plus h bar over 2 is the eigenvalue of SZ, times this minus gamma B0. So minus gamma B0 h bar over 2 would be the eigenvalue. So yeah, eigenvalue of the of this Hamiltonian for the spin up state. And conversely, for the spin down state, we get E minus equal plus gamma B0 h bar over 2. So it favors the spin up state because the magnetic field is in the up direction. So the spin up state has lower energy here. Okay, So, okay, so we know what the eigenstates are. So a general state, as it evolves in time, chi, will be some multiple of the spin up state plus some multiple of the spin down state. And the evolution in time works exactly like it did for all the other quantum systems we've seen. It's e to the minus I, the energy of that eigenstate, times t over h bar. Okay, so you can see if we plug in t equals 0 here, these exponentials both go to 1, and we get chi of 0 is a chi plus b chi minus, which is exactly what we had before. But we put in the time dependence here to look at what happens as time evolves to this to this spin state. Okay, so that becomes this, and we're going to let so if we write it out as a vector, where the top coefficient is the coefficient of chi plus spin up, and the bottom element of the vector is the coefficient of spin down, we get this. Where we've substituted in the values for E plus and E minus using these values up here. So, and then we're going to let, for reasons that'll become hopefully clear in a second, we'll let A equal cosine of alpha over 2 and B equal sine of alpha over 2. We know that A squared plus B squared has to be 1, and cosine squared plus sine squared is 1. So whatever A is, it has to be something between -1 and 1. So we can find an alpha that works. And then that will force B to be the sine of alpha over 2, so that the cosine squared plus sine is equal to 1, as it has to be. So this is no loss of generality here. Okay. So the expectation values, now that we have the state and time, the expectation values of Sx, Sy, and Sz are, well, we take the we sandwich the operator Sx between the complex conjugate, and it's not a star, it's a dagger, because this means turn this row into a column. So you take the complex conjugate, but you also turn this row into a this column, which is chi of t, into a row, which is chi of t dagger with complex conjugates, times Sx times this chi of t back again. And so if you multiply the Sx matrix, which we looked at before, by this row vector and then this column vector, and simplify, we get this here, h bar over 2 sine of alpha. So you can see we get alpha instead of alpha over 2, which is why we picked alpha over 2 here, times cosine of gamma b0t. Okay, we do a similar thing for Sy. We sandwich Sy between the row vector chi of t dagger and the column vector chi of t, and we do that vector matrix multiplication. We get, in this case, minus h bar over 2 sine of alpha sine of gamma b naught t. And then for Sz, if we do the same thing, we get Sz equal h bar over 2 cosine alpha. So the time dependence cancels out for the Sz, because these are Sc eigenstates. Okay, so what does this mean? Let's visualize this a little bit. Okay, so this is the vector S with components Sx, Sy, and Sz. This says that Sz, S will have a constant Sz, because it's just equal to the constant h bar over 2 times the constant alpha that we picked. So the Sz will be constant. So it's at the same height Sc, and S will be tilted at an angle alpha relative to the B field, because Sz is cosine of alpha, while Sx and Sy involve the sine of alpha, which is the opposite of this angle alpha. So this would be this vector here, whereas Sz would be this adjacent side here. Okay, so this is it has angle alpha relative to the B field, and whereas the Sc component stays constant, we see that there's a time dependence to the Sx and Sy. Sx goes as the cosine, Sx goes as the minus sign. And that has the effect of making this expectation value of S, the three components, precess around the magnetic field. So it'll circle the magnetic field. And that's actually exactly what happens when we have a classical magnetic moment exposed to a magnetic field. It will circle the magnetic field because of a torque that the magnetic moment feels in the presence of a magnetic field. Okay, so we get agreement with what happens to the expectation values of the spin with what happens to a classical magnetic moment, which is nice. Okay, so for our final example, we're going to look at an electron in a magnetic field again, but this is going to be a spatially varying magnetic field, and it's going to tie into a very important experiment called the Stern-Gerlach experiment. So it turns out in a spatially varying magnetic field, there's not only a torque that a dipole feels due to the magnetic field, but also a force on the magnetic dipole if the magnetic field varies. And the force is given by the gradient of mu dot b. Well, remember, mu dot b is minus mu dot b is the energy. So this force is, which is a vector, actually, this should be a vector, is minus the gradient of E or H. So it's going to point, the force is going to always move the, particle towards lower energy, because the gradient points in the direction of higher H and the minus gradient points in the direction of lower H. So this force acts to minimize the magnetic potential energy minus mu dot B. So this force can act to move or deflect particles with spin. Okay, so let's take an example. So we have a magnetic field XYZ with a small, alpha is a small constant, minus alpha x in the x direction, plus a rather large B0, plus a small z-dependent term, so that the magnetic field is not constant in space because it depends on z, but just a small amount. Okay. And you may wonder why we don't just put the z component in. Well, we have to put the x component in so that the divergence of b is 0. Which is a condition on B. So we have to introduce this little x component here to make it a valid magnetic field with 0 divergence. Anywho, the force turns out to be, if you apply this gradient of mu dot B on using mu equal gamma s on this function here and dot it with B, and go through a little bit of algebra, you get a force, which is the only terms which contribute are the terms with varying with x and z. The constant term doesn't, B0 doesn't contribute. So you get gamma alpha minus SXI plus SZK. Okay, well, SX is going to oscillate rapidly due to the Larmor precession around the magnetic field B naught K, which we saw before. So SX here is not going to be constant. It's going to, because we have a magnetic field in the Z direction, so SX is going to oscillate very rapidly around B naught K. So that tends to wash out the force. A time average of a very rapidly varying force is essentially 0. So we just get the last term, which is gamma alpha SZ in the Z direction. So we just have FZ equal to gamma alpha SZ. Okay, so we have a force here which acts in the Z direction, which can deflect particles moving through this magnetic field in the Z direction, moving them up and down in the Z direction. So classically, SZ here, if it was a classical angular momentum, it would take on a continuum of values. So with a continuum of values, we could get a continuum of forces, and we would expect if we sent a particle through, depending on its SC value, we would get a smear of of deflections. Depending on SZ, the force would vary continuously, so we'd get a smear of deflections. But in quantum mechanics, this is quantized, so we get a discrete number of spots where the particles with spin are deflected by the spatially varying magnetic field, because SZ can only take on the values plus or minus h bar over 2, okay? Or for a spin 1/2 system, it can only take on 2 values. So, in fact, observing 2 spots instead of a smear, two discrete spots for a beam of silver atoms in what was called the Stern-Gerlach experiment in the 1920s led to the original idea or hypothesis that particles could have half-integer spins. So it was originally an experiment that suggested, because of these 2 spots, that there were 2 values, possible values for SZ, and therefore it was a half-integer spin. And this gave Stern and Gerlach a nice Nobel Prize. And so this is just to conclude, we'll have a schematic here, which shows the beam of silver atoms coming in. Silver atoms wind up having a net spin of 1/2. And so they pass through the magnet. The magnet field, over here, the magnetic field becomes spatially varying. So they're deflected, but they're not deflected any amount, because the spin is quantized. They're deflected, and SZ is quantized. There's only 2 possible values of force that they experience, either FZ plus gamma alpha times h bar over 2, or FZ is gamma alpha times minus h bar over 2. So we get 2 spots, one for spin up and one for spin down. Okay, so that shows a beautiful experiment which shows the quantized nature of the spin. Okay, so just a quick summary. What have we done? We have looked at the intrinsic spin angular momentum. We've seen that all elementary particles have this intrinsic spin. We've seen that it doesn't depend on spatial variables. It's an intrinsic property of those particles. We've seen that we can write it that it's in a quantum system. It's a finite quantum system with a finite basis. And we looked at spin 1/2. We saw how we could write operators as matrices that were finite matrices for spin 1/2. Those were 2 by 2. And we saw how if a particle was in the spin up state, measuring spin x in the x direction gave 2 possibilities with equal probabilities. So we couldn't know SZ and SX with equal probability, with precision at the same time. And then we saw 2 examples, physical examples. We saw the Larmor precession, which comes about because of the interaction between the magnetic field and the intrinsic spin magnetic moment. And then we saw the Stern-Gerlach, which comes about because of the interaction with the intrinsic magnetic moment with a spatially varying field, giving rise to 2 possible deflection values. Okay. All right. Thanks for your attention, and I will see you in class.